All right, so let's begin. Firstly, we have this V Clubs update here. You guys can see we made some significant updates to the V Clubs, and we have like all the content since the beginning of the year. We have the thermodynamics activity and SAT videos. We have all the slides, right? All the slides, and we have like all the meeting recordings as well. And so like all the links are attached here, all the resources. If you were curious about any of the past stuff that we've covered, it's all here. So you guys can check some of this stuff out. And so it's a very important update for us. So now I'm going to share my screen, see if that works. All right, so today we're going to be discussing entropy and chaos. We already went through the V Clubs update. So first, we're going to start with like a review of the thermodynamics vocabulary activity. And so we're just going to review some of the key vocabulary that we were discussing in the first two lessons, right? So we had like the matching questions. Hopefully you guys at least took a look at the activity, as we did mention it a few times. So these are the matching questions. There were 11 matching questions. We have the internal energy, right? Remember the internal energy, if you guys remember this. The internal energy is the sum of the kinetic energy and potential energy of all particles in the system, right? So we have that U is KE plus PE, right? So you guys might remember that. And then, so temperature is measure of hotness or coldness indicating, so basically this is the matching activity here. And so we made this using the Quizlet. And so these are just the definitions, like adiabatic process and isobaric process. So hopefully you guys tried these questions out. I probably won't be rereading like all the definitions, but these are basically the answers here. And we will try to post these solutions here, right? A few key concepts are like kinetic energy is dependent on the temperature in thermodynamics, right? Or you have like extensive property depending on the extent of the system, right? So this is just reinforcing the key vocabulary here. We won't spend too long on this. But so now, this is something I left for you guys to try is the multiple choice questions. I'm hoping that you guys can answer some of these in the chat. So let's try number one, guys. Volume, is it A, B, C, or D? Try to leave response in the chat for this one. You can private message me. Yes, so this one's the answer choice C right here, right? Volume is the amount of space that was occupied by an object, right? So this is literally us when we were like in first grade, right? 6-year-old, 7-year-old. This is what we were saying. We were saying that the volume is the amount of space occupied by the object. All right, let's try number two. Number two is process that takes place at constant temperature. Which of these would it be? A, B, C, or D? All right, yeah, process that takes place at constant temperature is called an isothermal process, right? Iso means same, thermal refers to temperature, so you get isothermal process. Let's try number three. All right, so heat, this one's A. This one is, heat is the energy transferred due to temperature difference between the system and the surrounding in thermodynamics, right? C is radiation. This one's radiation. This one is, let's see, this one's convection right here. And then the second one is just internal energy. Number four, separates the system from the rest of the universe. All right, number four is the answer choice A, right? It's just surroundings. right? So you have, remember that you have the system surrounding, right? So this is just some enclosure. It's a bit weirdly drawn, but this is just the boundary right here, right? Is the boundary, which can be physical or hypothetical, right? And then everything around it is just the universe, everything around it. All right, let's go on to number 5, conduction, guys. What's conduction? Yeah, guys, sorry. For number 4, it would be the boundary, right? For the boundary, right. Sorry about that, guys. I was thinking about a different one. So we have the boundary, right? Just separating the system from the rest of the universe in this case, right? As shown by the visual diagram. I give the wrong answer choice, but the right explanation. So it would be a C, boundary. So I have to be careful with the multiple choice questions. So for conduction, we get C, right? Conduction, as we know, is just the transfer of thermal energy via touching, right? When two objects are in direct contact with one another. Let's try number 6. Hopefully, there's 11 multiple choice questions. Hopefully, we can get through this pretty quickly. So for number 6, this is this is an isolated system, right? Because it can exchange neither energy nor matter is the key word here, right? If it could just exchange energy but not matter, that's called a closed system. And if it can exchange both energy and matter, then that's called open system. All right, this is one regarding the sign conventions, number 7. What do we call heat supplied to the system? Basically, is that positive heat or negative heat when we supply it to the system? All right, so if we supply it to the system, it's positive heat. If heat is released by the system, that would be negative heat. And then let's try number 8, heat. All right, we kind of did number 8 already. Heat given off by system is a negative heat. All right, let's try number 9. Number nine has a bit of a mistake, actually. Number 9 is a mistake on our end. This is supposed to be the word by right here. So for number 9, it would be the answer choice. It would be answer choice C, actually, because this is another sign convention. Negative work is the work done by the system or expansion, while positive work is work done on the system or contraction. All right, number 10 is pressure. So give your answer for this one. Is it A, B, C, or D? So pressure is very famous, like in fluid dynamics, right? We talk a lot about pressure. And in thermodynamics as well. So a pressure is force divided by the area, right? So this would be answer choice B right here. This first one was radiation. The third one is volume from the previous ones. And then D, this one is the surroundings right here. Right, rest of the universe outside the system. All right, and then number 11 is state functions, right? So this one's actually a slightly challenging one. Would this one be A, B, C, or D? Just think about that for a moment. And then this one is just this isn't just the answer choice C. These are basically, we're emphasizing that these are path independent, right? Like the internal energy, entropy, and pressure. These are path independent. Like path dependent would be like heat and work, for example, right? So we're going to be releasing like the Quizlet to this so you guys can look at this in a lot more detail. These are the true false questions. They're pretty easy questions. Usually the false ones are mainly due to like random pairings. The true ones, I guess, are important, right? Like remember that pressure times the volume is the work, right? Change in the volume due to an application of external pressure. And so we're not going to go in very much detail into these true and false questions. You guys can check these out in the vocabulary activity afterwards. But let's move on to the next thing we have planned. We're going to start with some review regarding the idea of entropy. Entropy is randomness or molecular disorder. Right? We give the example of solid, liquid, and gas, right? Where the gas has the most entropy and like a more random configuration, and the solid is more fixed and has less entropy, right? And so the more entropy the object has, the harder it is to do work, right? And so we can show it to be the reversible heat over the temperature, right? But there's this famous configuration by Boltzmann here, right? Regarding the microscopic arrangements, omega. And then we have second law of thermodynamics. We were discussing a lot of this before break, that the entropy will increase. Right? Entropy will always tend to increase, right? Because you have the entropy total is the change in the entropy of the system plus the change in the entropy in the surroundings, which will always be like greater than zero or at best like equal to zero, right? So basically you can have like a group of like processes, right? Like in the ceiling fan example that we talked about, right? As to how the ceiling fan works, where you have like the hydroelectric power and a few like transformations of energy, right? But there's always some like waste energy that's going to be released as heat according to second law of thermodynamics. And so the entropy will always tend to increase, which is a key concept. And then this is a key theory of the entropy, which is the big chill theory, which is basically the heat death of the universe theory. Right? So the universe will eventually reach equilibrium and there's no thermodynamic free energy, right? So no energy will be available to do work, and then you have maximum energy, right? Or sorry, the maximum entropy. Maximum entropy at that point. So that was for the review right there. And so now we're going to get on to introducing some of the new ideas. We have introductory nonlinear dynamics, which we're going to discuss briefly. So if you remember if you see like the physics club trailer, most of the people here have probably seen the physics club trailer. We had this visual in the physics club trailer. Right, so we're going to be discussing what this was all about here. First, we're going to start with some basic terms. Right, dynamical systems are just the systems that are going to change over time, right? And then in nonlinear, it's just not linear. Not so when it's linear, you have like some kind of direct proportion, right? In a linear system, like the change in output is proportional to the change in input, right? So in a nonlinear system, that is not the case, right? The change in the output is not proportional to change in input, right? Chaos is where you have unpredictable behavior in something that's completely determined. That'll become a little bit more clear with some more examples. And we also have the idea of phase portrait or phase space, which is visual representation of possible states, trajectories, or solutions. So let's just do an example. So we're going to start with a mathematical example. So bear with me here. We have x prime equals to sine of x. Or instead of x dot, let's just do dx over dt. So this is like, this is the derivative is equal to the sine function. So this is basically, you can think of like a particle which has a velocity here, which is the sine of its displacement. And so if we were to try to, basically a solution to this would be like its displacement against time, right? So there's some concepts in physics 1 here as well, right? So it's like displacement against time would be the solution to this here. So if we were to try to analytically solve this differential equation, it would get quite rigorous, right? You don't have to completely follow along with the steps. We're doing some kind of separation of variables, very rigorous technique. You have to know a very difficult integral here, right? That this becomes like natural negative log of cosecant plus cotangent, which we're not going to go too much into depth into this, but the point to understand is it's just very rigorous, very complicated ideas here. And then this becomes, if you have like an initial condition at time t equals to 0, you have like x naught, right? And then you apply like log property. And then this just becomes cotangent x naught over cosecant x plus cotangent x. And basically the idea that you're supposed to get from this is very hard to extract any meaningful information from an expression like this, right? It's very hard to get some very meaningful data out of this, right? So we instead look to a more geometric approach. And put this all on one slide right here. So we look to a more geometrical approach for understanding what's going on. Instead, we're going to take our x prime, right? X prime is just dx over dt. The x dot is shorthand. So you take x prime equals to sine of x, right? And we're just going to graph x against x prime, making what's called a phase portrait or phase plane. Here's x prime axis, and here's the x-axis. So the sine of 0 is 0. Sine of pi is also 0. And let's try to shorthand this. Sorry, freehand this. And so graph looks a little something like that. All right, just a rough sketch right there. And so what we see is we see like different initial conditions for x against x prime, right? So basically you can see like there are places where it's under the axis, the horizontal axis, and you can see places where we're over the horizontal axis, right? So basically, for example, let's consider from like negative pi to 0, right? From negative pi to 0, what's happening is that the velocity is less than 0, so the position is going to decrease, right? But if the velocity was greater than 0, like for example from 0 to pi, right? The velocity is greater than 0, so the position will tend to increase, right? And so you can see, you can kind of look at it and just draw like an arrow, right? So you can think, like this, I'm just drawing like the arrows here. Right, so whenever it's under the axis, I just give like a left arrow. Whenever it's over the axis, I give like the right arrow. Hopefully you can kind of see that here. Minus 2 pi. And so you get what are called stable point. This is like a stable point right here, right? Because if you start from like negative 2 pi to pi, or you start from 0 to negative pi, you're going to always tend to this stable point right here. Versus here you have what's called an unstable point. We'll denote that with an empty circle, right? Where if you start somewhere near this point, you're always going to diverge away from this point. Similarly, there's another stable point right here. And that's all periodic in the sine function, right? So here you have to understand there's the stable and unstable critical points, right? And so now that we have this diagram here, we're more confident in graphing t versus x. So here we have like a t-axis, and here we have like the x-axis. Here's 0, pi, and 2 pi, right? And you can kind of think about this and piece this together. There's like a stable point at pi. So if you start at 0, and it's like the x prime right here, x prime can be like is 0, right? At any of the critical points. And so you can kind of think about piecing together like a trajectory like this. And it's there's a little bit, very complicated for now. It's a little bit complicated, but it's basically you can take this and piece together that basically. Right? You can use the fact that this is a stable point, right? So all of the trajectories will tend to this, right? And they're diverging away from 0 and away from 2 pi, right? Towards pi, basically. So this is just the idea of taking a geometrical approach as opposed to trying to work with this nasty expression up here. Next, we're going to talk about the pendulum. This is a phase portrait of the nonlinear pendulum without friction. So you have a pendulum, right? You have a pendulum, but there's no friction. So there's nothing stopping the pendulum. If you do like a free body diagram in the corner or something close to a free body diagram, you have like, you can have like the force of tension here, right? And then you have like the force of gravity over here, right? There's like mg right there, right? And what we do is we introduce what are called the polar coordinates, which make it a bit easier to analyze if you have like r hat here and you have theta hat. Over here, these are very special coordinates. Sorry, switch them. Pay attention. R hat is over here, and theta hat will be over here. Have to pay attention to our choice of coordinates. So here, the polar coordinates work a little bit different from the rectangular coordinates, as the coordinates are kind of like, they're in the frame of the pendulum. Those change as the position of the pendulum is changing. The angular position of pendulum is changing. So we can see along the radial direction, basically, there's a gravitational component radially, and there's like tension, and those kind of cancel out. So there's not very much meaningful information along the r hat direction, but along the theta hat direction, you have this component of gravity. You have this component of gravity, right? And you can basically, you can write like your equation, right? Like mx double dot is equal to negative mg sine theta using trigonometry, right? And so you get that kind of an idea. But basically, it's more important to use like your intuition here when you're thinking about the pendulum, right? So if your pendulum's not running out of energy, then there's some, like, it's just going to do the same thing, right? It's going to be periodic motion. So this is just becomes like a circle, right? It's like a circles here. There's a bunch of circular trajectories. It's not very well drawn. So we have like these circular trajectories. And so what this is showing is that it's just periodic, right? So the trajectories are always along here. So there are also these trajectories. So you can see like from the red point, all the red point is like circular trajectory is what this is trying to show. If you start over here. On the other hand, you have like this blue point, right? Which for pendulum, we typically use small angle approximation, right? So you don't get to go much further past the 15 degrees. Right? But if we use phase portraits instead, then we get to think a little more abstractly. So that could be like an example of basically if you give the pendulum, like, for example, you have like a high velocity here, right? Is what they're showing. You have really high angular velocity on our pendulum. And so what's going to happen is that the pendulum goes like over the top, right? You can imagine this. You have the pendulum and you're basically releasing with a very high velocity. It's just going to go over the top. There's a critical velocity somewhere here, but it just goes like over the top basically. Right? So like maybe around here you have like a critical velocity somewhere around there. And so the pendulum is just going to go over the top. So it's very important to just think like intuitively about the concept. If you have like a lower velocity and you just release it, the pendulum is just going to go without, there's no friction. It's going to go in circular periodic motion. Or otherwise, it's just going to go like over the top, right? So if you have like a nonlinear pendulum with friction now, right? Basically the result's always going to be the same, right? You release it with high velocity, you release it with low velocity. At some point, it's going to come to rest, right? Because energy is being dissipated by friction. Energy becomes dissipated by friction. It goes down. Right? And so if you wanted to draw, we don't have much time left, but let's quickly do this. So if you want to draw like a phase portrait of the pendulum, right? You would just basically start at some place and it spirals inward. So let's try to draw a spiral here. And so it just spirals inward, right? And so any trajectory basically spirals straight into the origin here. Because energy is always being dissipated from our system, which is key concept, right? So this becomes a fixed attractor right here. Fixed attractor. Right? It will attract all points in the system. And here's like this is theta against V, right? Position against the velocity here. Our phase portrait. Now we're going to talk about Edward Lorentz, who was a meteorologist who just wanted to try to understand the weather, right? He wanted to understand why weather was so difficult to predict in the future. If you look at like your weather reports, you don't get much further than like a week, right? You can't predict like next Wednesday's weather or something. So he tried making like a computer model, right? 12 equations, 12 variables about key things in the atmosphere and stuff that meteorologist has to deal with, along with thermodynamics ideas, right? Temperature, pressure, humidity, and other quantities. So he was printing basically against like time steps, right? Time steps and computer simulation. But we find that the printer actually rounds to 3 decimal places while computer calculated with 6, right? So basically he ran like a simulation one time and then he wanted to check like a mistake or something. So he ran it from its like halfway point, but he found completely different results, right? What happened was a divergence of his results because of this decimal places, right? So you can imagine it's very, very slight differences, 6 decimal places, 3 decimal places. You have what's called sensitive dependence on the initial conditions due to these changes, right? And so he wanted to understand more about this chaos that was occurring. So he made a simplified model of convection using what are called the Lorentz equations. And so here x is rate of convective motion, y is the temperature difference between ascending and descending currents, basically you have like the atmosphere that's just cooled at the top and then heated at the bottom is the idea. And then Z is distortion from linearity. We'll cover this in a bit more detail. And so we have just some fixed parameters, right? Like sigma, R, and B are just fixed parameters in the system describing like the unique weather states, right? So these are, again, thermodynamical and fluidodynamical properties. Right? And so what we see is that these equations also describe the motion of a certain water wheel. It's called the chaotic water wheel. And so this is a very cool concept, right? So you have a water flow at the top, and you have, all right, so we are running a bit short on time. Let's quickly, so basically it's the idea that you have water flow at the top, and you have these leaky paper cups, and so the cups are attached to the rim, and this cups can change direction. The wheel can change direction, right? And this is what this visual is trying to show. We're going to go in a bit more of detail next time. Just regarding a few more visuals, this is the same apparatus, but it's a slightly more complicated version of that. And so we're going to look at that in a little bit more detail. All right, I will stop the screen share for now. Let's take this link. All right, so I will put that link in the chat. So if you guys want to check that out, you guys can check that out. It shows the basic principle behind the water wheel and some of the chaotic behavior and how that thing is always like changing direction. So if you guys are very interested, you can check out that video. And we are going to be continuing just a few more visualizations of chaos theory afterwards. All right, guys, thank you so much for attending. Hopefully you guys enjoyed some of the stuff we talked about today. We're going to talk a little bit more about chaos and the visualizations, along with energy and some of the applications of thermodynamics next time. And then we'll continue everything with the review after that. Thank you, everyone.